Hello, and welcome to The Sleepy Scientist. It's lovely to have you here. Before we get started, I'd love to know where in the world you're listening from tonight. Maybe you're already tucked into bed, curled up on the sofa, listening through headphones in a quiet room, or simply winding down after a long day. Wherever you are, I hope you're comfortable, relaxed, and ready to let your thoughts drift somewhere a little stranger than usual. If you enjoy these slow, calming journeys through science, a like and a subscription really does help The Sleepy Scientist continue to grow. And if you're already subscribed, thank you. Your support means a great deal, and I'm very glad you keep coming back to spend these quiet hours with me. If you'd like to take a little of The Sleepy Scientist away with you, there's a QR code on screen for the first portion of tonight's video that will take you to the Sleepy Scientist ebook. You'll also find a link waiting quietly in the description whenever you feel like wandering over. And if you prefer to listen with your screen off and your eyes closed, we're now uploading episodes to Spotify as well, so you can drift along with these journeys wherever feels most restful to you. Tonight, we're exploring one of the most peculiar ideas in all of quantum physics. Superposition, the possibility that a quantum system can exist in a combination of different states, even when those states seem completely incompatible with the way the everyday world behaves. Along the way, we'll meet Schrödinger's famously unfortunate cat, look at why we never seem to see obvious superpositions in ordinary life, explore how decoherence quietly pushes the quantum world towards something more familiar, and see how quantum computers try to hold on to these fragile states long enough to make them useful. So get comfortable, let the room grow a little quieter, and we can begin. How can something exist in several possible states at once, when everything around us seems so determined to choose just one? The world around us seems remarkably committed to making up its mind. A lamp is either glowing or dark. A coin resting on a table shows heads or tails. A book is on the shelf or beside the bed. A planet follows one path through space, rather than several visibly different paths at once. Even when we do not know where something is, we normally assume that the object itself has a definite position and that our ignorance is the only problem. That assumption feels so natural that it barely seems like an assumption at all. Classical physics was built around this kind of certainty. An object has a state. Its position may be unknown to us, its speed may not have been measured, and its future motion may be difficult to calculate. But the underlying idea is that those properties are there to be found. The uncertainty belongs to the observer, not to reality itself. Quantum physics changes that picture in a very specific and rather uncomfortable way. A quantum system can be described by a state containing several possible outcomes together. This is what we mean by quantum superposition. It is not simply that we have lost track of the answer. It is not the same as covering a coin with your hand and wondering whether it landed on heads or tails. In that case, the coin has already chosen. You just do not know what it chose. A quantum superposition is different because the alternatives can remain connected through what physicists call coherence. Their probability amplitudes can influence one another, producing interference that ordinary uncertainty cannot reproduce. That word, amplitude, matters. Quantum theory does not normally describe a particle as a tiny solid object that splits into a collection of ordinary copies whenever several possibilities become available. Instead, the state of the system is represented by mathematical probability amplitudes associated with different possible outcomes. Those amplitudes contain more information than ordinary probabilities. They can reinforce one another or cancel one another. Two alternatives can contribute to an outcome in a way that increases its probability, while in another situation they can almost completely remove that outcome from consideration. This interference is one of the clearest signs that superposition is not just a fancy name for ignorance. Imagine that you place a marble beneath one of two cups while someone else looks away. From their perspective, the marble could be beneath the cup on the left or beneath the cup on the right. They might assign equal probabilities to both possibilities. But nothing strange has happened to the marble. It is under one cup. The situation in quantum mechanics can be fundamentally different. A particle can be prepared so that its quantum state contains an alternative associated with one location and another alternative associated with a different location. Until an interaction destroys the coherence between those alternatives, the two parts of the state can contribute together to later results. That does not mean the particle is secretly a very small marble smeared across two shelves. It means that the classical idea of a particle possessing one hidden definite state at every moment is not sufficient to reproduce what experiments actually show. And this is where the phrase "the state that should not exist" begins to make sense. Superposition does not violate quantum theory. Quite the opposite. It is built directly into the theory and has been tested through an enormous range of experiments. The thing it violates is our classical expectation about what a physical state ought to look like. According to everyday intuition, mutually exclusive possibilities should remain mutually exclusive. Something cannot be here and there in the same sense. A switch cannot be both on and off. A cat cannot be comfortably alive and inconveniently dead at the same time. Quantum mechanics tells us that the underlying mathematical description can contain combinations of alternatives that would be impossible for ordinary classical objects. At very small scales, the consequences are not subtle. Photons interfere. Electrons interfere. Atoms can be placed in superpositions of different internal states. Molecules can produce matter wave interference when they are isolated carefully enough from their surroundings. In laboratories, physicists routinely prepare quantum systems in states that would sound absurd if they were described using only the language of everyday objects. And yet when we look around the room, nothing seems remotely like this. Your chair is not obviously in several corners at once. The moon does not appear to follow several incompatible orbits around Earth. A cup of tea does not remain in a coherent combination of being on the table and on the floor, which is probably just as well. Somewhere between the carefully controlled quantum experiment and the warm, noisy world of ordinary life, something changes in the way those possibilities appear. The mystery is not that quantum systems can form superpositions. That part is experimentally established. The deeper puzzle is why the world we experience looks so definite. Why does a measurement seem to produce one result? What is actually happening to the other possibilities represented in the state? Why can scientists preserve coherence in tiny systems for useful periods of time, while a macroscopic object appears to lose that quantum delicacy almost immediately? And perhaps most importantly, is there really a sharp boundary between the quantum world and the classical world at all? Modern physics suggests that there may not be. The same quantum principles that describe electrons and photons are expected to apply to larger systems as well. What changes dramatically is how difficult it becomes to isolate those systems from their surroundings. A single atom can sometimes be protected from unwanted interactions with extraordinary care. A warm object containing an immense number of atoms is constantly colliding with air molecules, emitting thermal radiation, absorbing photons, vibrating internally, and interacting with its environment in countless ways. Those interactions matter because they can destroy the delicate phase relationships that make interference possible. This process will eventually lead us to decoherence, one of the most important ideas for understanding why obvious quantum superpositions disappear from everyday experience. But before that idea can become meaningful, there is a more basic distinction to keep hold of. Not knowing which outcome occurred is one thing. A coherent quantum combination of possible outcomes is another. Classical probability says that one answer exists, and we simply have not discovered it yet. Quantum superposition says that, before certain measurements or interactions, the physical state can contain several alternatives in a form that allows them to interfere. That difference sounds small when stated in a sentence. In physics, it changes almost everything. Possibility and superposition can sound almost identical when we first meet them. If we do not know the result of something, we usually say that several possibilities remain open. A coin hidden beneath a hand might be heads or tails. A playing card placed face down on a table could be a king, a 7, or an ace. Until we look, several answers seem possible. But in classical physics, those possibilities exist only in our knowledge. The coin has already landed, the card already has a face printed on it. Our uncertainty does not mean that the object itself is somehow divided between several physical conditions. This distinction becomes much sharper if we think about what physicists mean by a state. In classical physics, the state of an object is meant to provide a complete physical description. Depending on the system, that might include its position, velocity, orientation, temperature, electrical condition, and other measurable properties. If all of those quantities were known precisely enough, classical theory would regard the object as occupying one definite state. We might fail to know that state, but the state itself is still assumed to exist. Probability enters because our information is incomplete. Suppose a coin has been tossed behind a screen. We know there are two possible outcomes, and if the coin is fair, we might assign equal probability to heads and tails. But this is a statistical description of our ignorance. Somewhere behind the screen, the coin is already showing one side. Physicists call this kind of situation a statistical mixture. A quantum superposition is not the same thing. Imagine a quantum system with two possible measurement outcomes. In a statistical mixture, the system has effectively been prepared in one state or the other, but we do not know which. In a coherent superposition, the quantum state contains probability amplitudes associated with both alternatives, and those amplitudes retain a definite relationship with one another. That relationship is called relative phase. Relative phase is one of the features that makes quantum probability so different from ordinary probability. Classical probabilities are simply added. If two mutually exclusive routes can lead to the same result, we calculate the probability associated with each route and combine them. Quantum amplitudes behave differently. They can reinforce one another, producing constructive interference. They can also oppose one another, producing destructive interference. In some arrangements, two individually possible alternatives can combine in such a way that a particular outcome becomes extremely unlikely or even impossible. That behavior cannot be reproduced by saying that the system secretly chose one alternative and we merely failed to discover which one. Interference is therefore one of the most useful experimental signatures of genuine coherence. If the alternatives can still interfere, we are dealing with something more than an ordinary mixture of possibilities. There is a mathematical language that makes this distinction especially clear. Quantum physicists often describe states using something called a density matrix. There is no need to imagine this as a physical object. It is simply a mathematical tool that records the probabilities and coherence present within a quantum state. For a coherent superposition, the density matrix contains information describing the phase relationships between different alternatives. When coherence is lost, those parts of the mathematical description disappear, leaving something that behaves much more like an ordinary statistical mixture. This later becomes extremely important when we consider decoherence, because interaction with the environment can transform a locally observable superposition into something that looks almost indistinguishable from classical uncertainty. There is another subtlety that makes superposition even stranger. Whether a state is described as a superposition depends on the basis in which we choose to describe or measure it. A measurement basis is essentially a particular set of possible outcomes used to describe the quantum system. A state can be perfectly definite in one basis and a superposition in another. Polarized light provides a gentle example. A photon can be prepared with a definite polarization relative to one orientation. If we measure it using a device aligned with that same orientation, its state can be described as definite with respect to that measurement. Rotate the measurement basis, however, and the same photon state can now be represented as a superposition of the two possible outcomes associated with the new orientation. Nothing mysterious has suddenly happened to the photon simply because the laboratory equipment was turned. The description has changed because the possible outcomes we are asking about have changed. This basis dependence is why the phrase "a particle is in superposition" can sometimes be too vague on its own. A more complete statement asks, a superposition of which states? Relative to which measurement? That small clarification prevents a great deal of confusion. It also reveals why quantum physics cannot be understood simply by imagining particles as ordinary objects behaving badly. The deeper difference lies in the structure of the quantum state itself. Classical probability describes uncertainty about which definite possibility is real. Quantum superposition preserves amplitudes for several alternatives in a coherent relationship, allowing those alternatives to influence one another through interference. The distinction may sound technical, but it is the foundation of almost everything strange that follows. Once experiments began revealing interference where classical alternatives should merely have added together, physicists were forced to consider a remarkable possibility. Nature was not simply hiding the answer from them. At the quantum scale, the familiar idea that one definite answer must already exist was itself becoming difficult to defend. Long before quantum mechanics existed, light had already begun to make physicists uncomfortable. For centuries there had been arguments over whether light should be understood as a stream of particles or as some kind of wave. Both pictures seemed to explain certain observations, but neither settled everything completely. One of the most important clues came from Thomas Young in the early 19th century. Young allowed light to pass through two narrow openings and observed the pattern that formed beyond them. If light behaved only like a collection of tiny classical particles, one might expect two bright regions corresponding roughly to the two openings. Instead, Young saw something more intricate. There were alternating bright and dark bands. This is the characteristic signature of interference. When two ordinary waves overlap, their effects can combine in different ways. Where the peaks of the waves arrive together, they reinforce one another and produce a stronger result. Where the peak of one wave meets the trough of another, they can partially or even completely cancel. Water waves do this. Sound waves do it. And Young's experiment strongly suggested that light did it too. The wave picture became even more convincing during the 19th century through the work of James Clerk Maxwell. Maxwell showed that electricity and magnetism could be described as parts of one unified electromagnetic theory. His equations predicted waves travelling through space at a speed that matched the measured speed of light. The implication was extraordinary. Light itself appeared to be an electromagnetic wave. For a while, this looked like a remarkably satisfying answer. Optics, electricity, and magnetism had been drawn together into one elegant classical framework. Light could reflect, refract, diffract, and interfere, because waves naturally behave in these ways. But toward the end of the 19th century, problems began to appear. One of the most serious involved thermal radiation. Classical physics attempted to predict how objects should emit electromagnetic radiation at different frequencies as they were heated. At lower frequencies, the calculations worked reasonably well. At higher frequencies, however, the classical prediction became absurd. It suggested that the emitted energy should increase without limit as the frequency rose. This became known as the ultraviolet catastrophe. Real objects, fortunately, do not behave this way. An ordinary hot object does not release an infinite amount of ultraviolet radiation, which would make sitting beside a fireplace considerably less relaxing. In 1900, Max Planck found a way to reproduce the observed spectrum of thermal radiation. He proposed that energy was exchanged in discrete amounts rather than in an indefinitely divisible continuous flow. The energy associated with each amount depended on the frequency of the radiation. These discrete units became known as energy quanta. Planck's proposal was initially introduced as part of a mathematical solution to a difficult radiation problem, but it opened a door that classical physics would never manage to close again. A few years later, Albert Einstein pushed the idea further. In 1905, Einstein examined the photoelectric effect, in which light shining on certain materials can eject electrons from their surfaces. Classical wave theory seemed to suggest that sufficiently intense light should eventually transfer enough energy to release electrons, regardless of its frequency. Experiments showed something different. Below a certain frequency, increasing the intensity did not cause the expected electron emission. Above the threshold frequency, electrons could be released even when the light was relatively weak. Einstein explained this by proposing that light transfers energy in discrete packets. Each packet carried an amount of energy determined by the frequency of the light. These packets would later be called photons. Now, physics had acquired a rather awkward problem. Light could produce interference patterns associated with waves, yet it could also exchange energy in discrete units associated with particles. It is tempting to imagine that light simply switches identity depending on the experiment, becoming a wave for one occasion and a tiny particle for another. That picture is useful only up to a point. A photon is not a miniature classical billiard ball that occasionally remembers how to ripple. Nor is it simply a conventional wave that somehow condenses into a particle at convenient moments. Quantum theory eventually replaced both classical pictures with a more general description. The quantum state assigns probability amplitudes to different possible outcomes, and the old double-slit experiment becomes particularly revealing when viewed in this language. Suppose a photon approaches two available paths through an apparatus. Quantum theory does not require us to assign the photon one hidden classical route and then blame our ignorance for not knowing which route it followed. Instead, the state can contain an amplitude associated with one path and another amplitude associated with the other. Those amplitudes are combined. Their relative phase determines whether they reinforce one another or cancel in different regions of the detector. The result is interference. The most striking part is that this behavior does not require a crowd of photons moving through the apparatus together. Experiments can reduce the intensity of the light so dramatically that photons are detected one at a time. Each individual detection appears at a particular location. One photon arrives, then another, then another. At first, the positions seem scattered, but after many individual events have accumulated, the familiar interference pattern gradually emerges. This means the pattern cannot simply be explained as different photons bumping into one another, or producing ordinary collective wave behavior through mutual interaction. The quantum probabilities for each individual event already contain the structure of interference. That is the historical point at which the familiar image of an ordinary wave spreading through space begins to give way to something more subtle. Quantum amplitudes can be associated with alternative possibilities. Those amplitudes can interfere. And when a measurement is finally made, one definite event appears. Light had not merely complicated the classical picture. It had begun to reveal a completely different way in which nature could organize possibilities. And once physicists realized that light could behave this way, an even stranger question became almost unavoidable. Perhaps matter could do it too. Once light had begun to behave like both a wave and something particle-like, the natural next question was whether matter might possess a similar dual character. That possibility became much more serious in 1924, when the French physicist Louis de Broglie proposed something remarkably bold. If light, which had long been described as a wave, could sometimes behave as though it arrived in discrete particles, perhaps matter, which had long been treated as particles, might also possess wave-like properties. De Broglie suggested that every material particle should have an associated wavelength. That wavelength depends on the particle's momentum. More precisely, the de Broglie wavelength becomes shorter as momentum increases. A slowly moving lightweight particle can therefore have a wavelength large enough to reveal measurable interference, while the corresponding wavelength of an ordinary macroscopic object is generally unimaginably tiny. For an electron, this can matter enormously. For a tennis ball, a cup, or a person walking across a room, the wavelength is so small that detecting any interference associated with its motion would be effectively impossible under everyday conditions. This was not merely an interesting mathematical suggestion. It could be tested. A few years later, Clinton Davison and Lester Germer were studying electrons scattered from the surface of a nickel crystal. Their experiment was not originally designed as a dramatic demonstration of matter waves, but the results became one of the clearest early confirmations of de Broglie's idea. The electrons did not scatter in the simple pattern expected from tiny classical particles bouncing randomly from a surface. Instead, strong peaks appeared at particular angles. The arrangement resembled diffraction, the kind of behavior produced when waves interact with a repeating structure. The regularly spaced atoms inside the nickel crystal acted somewhat like a natural diffraction grating. The measured electron pattern matched the wavelength predicted by de Broglie's relationship. Matter, apparently, could interfere. At roughly the same time, George Paget Thomson independently demonstrated electron diffraction by passing electrons through thin metal foils. There was a particularly satisfying historical twist in this. George Paget Thomson was the son of Joseph John Thomson, whose work at the end of the 19th century had helped establish the electron as a distinct particle. One generation had helped reveal the electron's particle-like character. The next helped reveal its wave-like behavior. Physics occasionally has a sense of humor about family history. The conclusion, however, was more profound than simply saying that electrons sometimes look wavy. An electron could no longer be adequately understood as a microscopic classical ball following one perfectly definite path through every experiment. The interference behavior suggested that quantum possibilities had to be combined in a wave-like way, but this did not mean that an electron was literally made from some ordinary substance smeared through space like a faint mist. The wave associated with quantum mechanics is not simply a material ripple. Instead, quantum theory describes the electron using a wave function. the wave function provides probability amplitudes associated with different possible measurement outcomes. Those amplitudes can spread, evolve, and interfere with one another. When an electron is finally detected, however, the detector does not usually register a diluted fraction of an electron spread over a wide area. It records a localized event. The strange combination is therefore familiar by now. Wave-like evolution, particle-like detection, and probability amplitudes connecting the two. This behavior turned out not to be unique to electrons. Neutrons have produced interference patterns. Atoms have been sent through interferometers and made to follow coherent alternatives. Increasingly large molecules have also demonstrated matter-wave interference under carefully controlled laboratory conditions. These experiments are especially important because they show that quantum superposition is not some peculiar trick, belonging only to photons or isolated electrons. The principle extends to composite objects containing many individual particles. The difficulty is preserving coherence. As systems become larger and more massive, several problems appear at once. Their de Broglie wavelengths become extremely short for ordinary momenta. Producing experimentally useful separations between alternative paths becomes harder, and larger objects generally interact more strongly with their surroundings. Air molecules collide with them. Thermal radiation can carry information away. Internal vibrations create additional opportunities for unwanted interactions. Each of these effects makes observable interference more difficult to preserve. This is why the absence of visible matter waves in daily life does not mean that quantum mechanics suddenly switches off above some familiar size. A person walking across a room has a de Broglie wavelength, at least according to the same quantum relationship that applies to an electron. It is simply so fantastically small, while the person is simultaneously interacting with such an enormous environment, that observing a coherent interference pattern would be beyond anything resembling ordinary experience. The difference between an electron and a chair is therefore not that one belongs to quantum mechanics, while the other has escaped from it. The difference is largely one of scale, isolation, complexity, and interaction. By the late 1920s, the experimental lesson was becoming difficult to avoid. Wave-like quantum behavior was not confined to light. Matter itself could diffract and interfere. The old distinction between wave and particle was beginning to look less like a fundamental division in nature and more like a limitation of classical language. What physicists now needed was a theory capable of describing these strange states consistently. A theory in which matter waves could evolve, a theory in which alternatives could combine, and a theory in which the strange possibilities revealed by experiments could be translated into precise predictions. That theory would place the wave function at the center of quantum mechanics. By the middle of the 1920s, the strange behavior of light and matter had become impossible to treat as a collection of isolated curiosities. Physicists now had strong evidence that electrons could diffract, that light could interfere, and that neither familiar classical waves nor familiar classical particles could provide a complete description of what experiments were showing. What was needed was a mathematical framework capable of describing this new behavior from the beginning. In 1926, Erwin Schrödinger developed one of the central formulations of quantum mechanics. His approach became known as wave mechanics, and at its heart was the Schrödinger equation. The Schrödinger equation describes how the quantum state of an isolated system changes with time. In classical mechanics, equations of motion might tell us how a particle's position and velocity evolve. In quantum mechanics, the corresponding object is the wave function. The wave function is not simply a picture of a tiny object rippling through space. It is a mathematical description containing probability amplitudes. Depending on the physical problem, those amplitudes can be associated with possible positions, momenta, energies, spin states, paths through an experiment, or other measurable properties. This is where quantum mechanics begins to separate itself very clearly from ordinary probability. A wave function does not directly tell us that a particle has a certain probability of being in one place and another probability of being somewhere else. First, it assigns amplitudes. The probability comes from those amplitudes. Max Born provided the crucial interpretation later in 1926. Born proposed that the wave function should be connected to probabilities through what is now called the Born rule. In spoken form, the essential relationship is simple. The probability of a particular outcome is given by the squared magnitude of the probability amplitude associated with that outcome. That extra step matters enormously. Probability amplitudes can carry information that ordinary probabilities do not, including phase. Two amplitudes can therefore combine before their squared magnitudes are converted into measurable probabilities. If their phases line up appropriately, they can reinforce one another. If their phases oppose one another, they can cancel. This is why quantum interference is possible. The mathematics does not merely keep a list of alternative outcomes, it allows those alternatives to influence the probabilities that eventually appear. Another important feature of the Schrödinger equation is its linearity. In simple terms, if one quantum state is an allowed solution, and another quantum state is also allowed, then a suitable combination of those states is allowed as well. That statement is the mathematical heart of the superposition principle. Superposition was not invented afterwards as a philosophical explanation for a few mysterious experiments. It is built directly into the structure of the theory. If a system can occupy one state, and it can occupy another state, quantum mechanics permits coherent combinations of those states under the appropriate conditions. This becomes especially powerful because there is no single universal way in which the same quantum state must always be described. Paul Dirac helped place quantum mechanics into a more abstract and general mathematical form. Instead of tying the theory entirely to waves drawn through ordinary space, Dirac's state vector approach allowed the quantum state to be treated more generally. The same state could be represented using different sets of possible measurement outcomes, known as different bases. For example, a state might be described in terms of position. The same state could instead be described in terms of momentum. A two-state system might be expressed relative to one spin direction, or relative to another. The underlying quantum state remains the same, while the mathematical components used to represent it change with the basis. This is one reason visual descriptions of quantum mechanics can become misleading so quickly. When someone says that a particle is in two places at once, the phrase can be useful as a rough introduction, but it is not the full meaning of superposition. A more precise statement would be that the quantum state contains coherent amplitudes associated with different possible position outcomes. And position is only one possibility. A system may be in a superposition of different energy states. It may be in a superposition of different spin states. A photon may be described as a superposition of different polarization states. A particle travelling through an interferometer may have amplitudes associated with different paths. The common feature is not physical duplication. It is the mathematical combination of alternatives within one quantum state. The magnitude of each amplitude helps determine how strongly that alternative contributes to the possible outcomes. The phase determines how different amplitudes combine. Two states with the same amplitude magnitudes can therefore produce very different experimental results if their relative phases are changed. This is one of the deepest differences between a genuine quantum superposition and an ordinary uncertain mixture. The phase can affect what actually happens. And yet, for all the astonishing accuracy of this framework, the wave function remains conceptually difficult. Physicists agree extraordinarily well about how to calculate with it. The Schrödinger equation has been used to explain atomic spectra, chemical bonding, semiconductor behavior, lasers, and an enormous range of laboratory phenomena. What the wave function ultimately represents, however, is still debated. Some interpretations treat it as closely connected to physical reality. Others understand it more as a description of information, expectations, or relations between systems. Quantum mechanics is therefore unusual in having a mathematical engine of extraordinary precision while leaving room for disagreement about what that engine is describing underneath. For understanding superposition, though, one point is already firm. The wave function is not simply a catalogue of answers waiting to be uncovered. Its amplitudes can combine. Their phases can interfere. And because the underlying equations are linear, combinations of allowed states are themselves legitimate quantum states. Superposition is therefore not an accidental oddity sitting at the edge of quantum physics. It is woven into the mathematics from the beginning. Superposition is often introduced with phrases that sound wonderfully dramatic. A particle is in two places at once. A system exists in several states simultaneously. Every possibility is happening together. These descriptions can be useful for getting the general flavour of the idea, but they are not quite precise enough on their own. In quantum mechanics, a superposition is a valid quantum state formed from a coherent linear combination of other possible states. That sounds technical, but the idea becomes clearer if we unpack it slowly. Suppose a particle can be detected in one region of space or another. Quantum theory allows us to prepare a state containing a probability amplitude associated with the first region and another amplitude associated with the second. The particle is not best imagined as a tiny solid object that has somehow duplicated itself. There are not necessarily two miniature versions of the particle sitting patiently in different locations. Instead, there is one quantum state containing amplitudes for different possible measurement outcomes. The important word here is coherent. Coherence means that the different components of the state retain a well-defined phase relationship with one another. That phase relationship is what allows interference to occur. If the alternatives lose coherence, perhaps because information about them escapes into the environment, the system begins to behave much more like an ordinary statistical mixture. So a genuine superposition is not simply a list of things that might happen. It is a structured combination of possibilities whose amplitudes can still influence one another. Imagine a particle whose state contains two spatial alternatives. One amplitude is associated with finding the particle toward the left. Another is associated with finding it toward the right. Before a position measurement, quantum mechanics may describe both alternatives as components of the same state. Then a detector is used. Perhaps it is an electronic position detector. Perhaps it is a photographic plate capable of recording a tiny localized interaction. The detector does not ordinarily produce a faint half mark on the left and another half mark on the right. Instead, a particular measurement produces one definite record. The particle is registered at one location. If the experiment is repeated many times using identically prepared systems, the overall distribution of those results follows the probabilities predicted from the quantum amplitudes. This distinction between the state before measurement and the definite record after measurement sits at the center of quantum theory. And there is another subtlety that makes superposition even more interesting. A quantum state is never meaningfully described as simply being in superposition without asking what states it is being compared with. Superposition depends on the basis being used. Consider quantum spin. A particle can be prepared in a state that is definite relative to one direction of measurement. If we choose that same direction, there may be one certain outcome. But if we describe or measure the same state relative to a different direction, it can appear as a superposition of the possible spin outcomes associated with that new measurement. So one description may call the state definite, another may express it as a superposition. Nothing has become inconsistent. The basis has changed. This is why statements such as the particle is in two states at once should always be treated carefully. The useful question is, which two states? Relative to which measurement? Once those details are supplied, the idea becomes much less mystical. Phase provides another part of the story. Every component in a superposition has an amplitude, and that amplitude carries both a magnitude and a phase. The overall phase shared by an entire quantum state is called the global phase. In standard quantum mechanics, changing only that global phase does not alter measurable predictions. Relative phase is different. The phase difference between components can change experimental outcomes because it determines how amplitudes interfere. Two components with one relative phase may reinforce each other, change the relative phase, and they may partially cancel. Under the right conditions, they can cancel completely for a particular outcome. This possibility has no direct equivalent in ordinary classical probability. If there are two classical routes leading to the same destination, their probabilities simply add. Quantum amplitudes must be combined first. Only after that combination do we convert the result into a probability. Because amplitudes can cancel, two available quantum alternatives can sometimes make an outcome less likely than either alternative would have made it on its own. That is one of the clearest signs that we are not dealing with hidden classical possibilities. The alternatives interact mathematically through interference. This is also why the phrase "every possibility happens at once" can become misleading. Quantum mechanics does not say that every imaginable event literally occurs together in the ordinary classical sense. A superposition contains particular components defined relative to a chosen basis. Those components carry amplitudes, their relative phases matter. And measurement produces outcomes according to rules determined by the quantum state. The theory is strange enough without making it stranger than necessary. What matters most is that superposition has measurable consequences. If the alternatives remain coherent, they can interfere. If information about those alternatives becomes available in a way that destroys coherence, the interference changes or disappears. That difference can be observed experimentally. So superposition is not merely a philosophical label attached to something we cannot see. It changes probabilities in ways that can be measured with extraordinary precision. A quantum state can contain several coherent alternatives. Those alternatives can reinforce one another, they can cancel one another, and the final pattern cannot generally be reproduced by pretending that one ordinary classical possibility secretly existed all along. This is what superposition actually means. Not several tiny copies of the same object, not simple uncertainty, not every conceivable reality piled together, but one quantum state containing coherent amplitudes for different possible outcomes, with phase relationships that allow those possibilities to interfere. And when those consequences are revealed in an experiment, the abstract mathematics suddenly becomes something we can see. The double-slit experiment is one of the clearest places where quantum superposition stops being an abstract idea and begins to leave a visible trace. Imagine sending a stream of particles toward a barrier containing two narrow openings. Beyond the barrier sits a detector capable of recording where each particle arrives. If the particles behaved like ordinary classical objects, the simplest expectation would be straightforward. Some would travel through the left opening, others would travel through the right. Over time, the detector would build up two overlapping bands corresponding to those two routes. Quantum mechanics predicts something very different. When the experimental conditions preserve coherence, the quantum state contains a probability amplitude associated with passage through one opening and another amplitude associated with passage through the other. Those alternatives are not treated as two independent classical possibilities. They are combined, and because they remain coherent, they can interfere. This becomes especially striking when particles are sent through the apparatus one at a time. Each detection still appears as a single localized event. One electron arrives at one point on the detector, then another appears somewhere else. Nothing about an individual arrival looks like a smeared-out wave, but as more and more detections accumulate, a pattern slowly emerges. Some regions receive many particles, other regions receive fewer, and certain bands receive almost none at all. The completed pattern resembles the interference produced by waves. This behavior was demonstrated for electrons in increasingly clear forms during the 20th century. Klaus Jinson carried out an important electron interference experiment in the early 1960s, using narrow slits to demonstrate the wave-like behavior of electrons. Later, Akira Tonomura and his colleagues produced especially memorable experiments in which individual electrons were detected one by one, while an interference pattern gradually assembled over time. The significance is difficult to avoid. If every electron simply travelled through one slit or the other as an ordinary hidden classical particle, we could assign a probability to the left route and a probability to the right route. Those probabilities would add. But adding those classical probabilities does not produce the observed pattern of alternating reinforcement and suppression. Quantum theory instead combines amplitudes. Where the amplitudes associated with the two paths arrive with suitable relative phases, they reinforce one another. This is constructive interference. Where their phases oppose one another, they partially or completely cancel. This is destructive interference. In some locations, the probability of detection can become extremely small even though either slit, opened by itself, would allow particles to arrive there. That is a remarkably non-classical result. Opening an additional route can sometimes reduce the chance of arriving somewhere. The explanation lies not in ordinary probability, but in the interference of quantum amplitudes. There is another revealing variation of the experiment. Suppose a detector is added that can determine which slit the particle passed through. If reliable which path information becomes available, the interference pattern disappears. This does not require a human being to sit nearby and consciously inspect the detector. The crucial event is physical. The particle interacts with another system. Information about the path becomes correlated with the measuring device or surrounding environment. In quantum language, the path can become entangled with the detector. Once the two alternatives have left distinguishable records, their ability to interfere is reduced. This is why the popular phrase observation changes the result can be misleading. Quantum mechanics does not require a mysterious conscious observer staring sternly at the experiment. What matters is interaction, information, and distinguishability. Niels Bohr connected this kind of behavior with the principle of complementarity. An experimental arrangement designed to preserve clear interference does not simultaneously provide complete information about which path was taken. Conversely, an arrangement that reveals the path sacrifices the full interference pattern. These are not simply two pieces of information that happen to be inconvenient to obtain together. They arise from different physical arrangements of the experiment, and the transition does not always need to be perfectly abrupt. If the path information is only partial, the interference pattern can remain partially visible. As the two routes become more distinguishable, the contrast between bright and dark interference regions generally weakens. As path distinguishability decreases, stronger interference can return. This gradual trade-off is more accurate than imagining a magical switch labelled observed and unobserved. The double slit therefore gives us an operational meaning for superposition. Before detection, the alternative paths can contribute together to the probability of a later result. Their amplitudes reinforce and cancel. Then the detector records one definite event. The individual particle does not arrive in two places, yet the statistics of many individual arrivals reveal that the alternatives were not behaving like separate classical possibilities. That is the strange balance at the heart of the experiment. One outcome appears, but the route toward that outcome contains the fingerprints of several coherent alternatives, and spatial paths are only one way to create this situation. Quantum systems can also be placed in superpositions of internal properties. One of the most useful examples is spin. There, the alternatives can be controlled with remarkable precision, making superposition less about two openings in a barrier and more about the internal state of a single quantum system. Spin is one of those quantum properties whose name is slightly unfortunate. It sounds as though a particle should be imagined as a tiny ball rotating around its own axis, rather like a miniature planet. But quantum spin is not ordinary rotation. Electrons, photons, atoms, and other quantum systems can possess intrinsic angular momentum even when there is no meaningful little surface spinning through space. The word spin survives because some of its mathematical behaviour resembles angular momentum in classical physics. But the resemblance only goes so far. One of the earliest experiments to expose this strange property was performed in 1922 by Otto Stern and Walther Gerlach. They sent a beam of silver atoms through a magnetic field that varied in strength across space. If the atoms possessed magnetic orientations distributed continuously, as classical intuition suggested, the beam should have spread into a continuous band. Instead, it separated into distinct components. The result revealed that the relevant angular momentum could take only certain allowed orientations when measured along a chosen direction. In the modern quantum description of the silver atom used in the experiment, the effect is closely connected to the angular momentum of its unpaired electron. This discreteness is one of the defining characteristics of quantum spin. For a simple spin one-half particle such as an electron, a measurement along a particular axis produces one of two possible results. These are conventionally described as spin up and spin down relative to that axis. The words up and down can be misleading if taken too literally. They do not mean that the electron contains a tiny arrow permanently pointing toward one side of the room. The result is defined relative to the direction chosen for the measurement. Suppose an electron is prepared so that its spin is definitely up when measured along a vertical axis. If we immediately measure it again along that same axis, quantum theory predicts the same result with certainty in the ideal case. But now imagine measuring the very same state along a horizontal axis. Relative to this new measurement basis, the state that was definite before is described as a superposition of horizontal spin up and horizontal spin down. In other words, being definite in one basis does not mean being definite in every possible basis. This is a beautiful example of why superposition is always a statement about a state relative to a particular set of alternatives. A quantum state can be perfectly well defined while still being expressible as a superposition when we choose a different basis. Physicists often represent the possible pure states of a two-level quantum system using something called the Bloch sphere. Despite the name, this is not a tiny sphere hiding inside the particle. It is a mathematical picture. Two opposite points can represent the two basis states, while other points on the sphere represent coherent superpositions of those states, with different relative amplitudes and phases. The Bloch sphere is useful because it turns an abstract quantum state into something that can be visualized as a direction. Moving around this mathematical sphere corresponds to changing the superposition. And unlike a particle traveling through ordinary three-dimensional space, these movements can be deliberately controlled. During the 20th century, Isidor Isaac Rabi developed powerful techniques for manipulating quantum states using oscillating electromagnetic fields. Rabi showed that atoms and nuclei could be driven between different quantum states when exposed to radiation at the appropriate frequency. Norman Foster Ramsey Jr. later developed the separated oscillatory field method, which allowed quantum phases and transition frequencies to be measured with extraordinary precision. These ideas became fundamental to atomic clocks, magnetic resonance, precision spectroscopy, and eventually quantum information science. In a carefully controlled two-state quantum system, an electromagnetic pulse can change the state in a predictable way. A pulse of one duration might transform a definite basis state into a balanced superposition of two alternatives. Another pulse can change the relative phase between those components. A later pulse can then recombine the alternatives so that their amplitudes interfere. Nothing needs to draw a bright and dark fringe pattern on a screen. The interference appears in the statistics of repeated measurements. Prepare the same system many times, apply the same sequence of pulses, and measure it. Then alter the phase or timing slightly, and repeat the procedure. The proportions of the two possible outcomes rise and fall in a regular pattern. That changing probability is the signature of quantum interference. The two components of the superposition have remained coherent long enough for their relative phase to affect the final result. This is one reason spin and other two-level systems are so useful. They provide a remarkably clean laboratory for studying superposition, without needing to picture a particle travelling through two widely separated slits. The alternatives can be internal quantum states. The system can be manipulated with carefully controlled fields, the relative phase can be adjusted, and the interference can be read out through repeated measurements. This two-level structure is also the foundation of the quantum bit. A classical bit is usually assigned one of two definite values. A quantum bit can instead occupy a coherent superposition of two chosen basis states, with its behavior controlled through precisely the same kinds of rotations and phase changes used in spin experiments. Yet one puzzle remains untouched by all this control. However carefully the superposition is prepared, and however elegantly its components interfere, the final measurement still produces a definite result. A detector does not usually report a vague compromise between spin up and spin down. It records one outcome. Repeat the experiment and the frequencies follow the quantum probabilities with remarkable accuracy. But each individual measurement appears definite. So quantum mechanics can tell us how to create a superposition, how to rotate it, how to preserve its phase, and how to predict the probabilities of its possible outcomes. The more difficult question is why a world described by coherent alternatives repeatedly presents us with one result at a time. Quantum mechanics contains a curious tension at its very heart. When a quantum system is isolated, its wave function evolves smoothly according to the Schrödinger equation. The evolution is deterministic in the sense that, Once the initial quantum state and the relevant physical conditions are specified, the equation tells us how that state changes with time. Nothing in this ordinary evolution suddenly chooses one possibility and discards the others. A superposition remains a superposition. Its amplitudes change, its phases evolve. Different components can spread, rotate, reinforce one another, or cancel. Then a measurement is made, and suddenly the description seems different. Instead of a smooth combination of possibilities, the experiment produces one definite result. A detector clicks in one place. A spin measurement produces one allowed value. An atom is found in one energy state. The transition between these two descriptions is the source of what became known as the quantum measurement problem. In the traditional textbook formulation of quantum mechanics, measurement is handled through a rule often called the projection postulate or collapse postulate. Before measurement, the quantum state may contain several possible outcomes. When the measurement occurs, the state is said to collapse onto the state corresponding to the observed result. The probability of obtaining each possible result is calculated using the Born rule. This procedure works extraordinarily well. If the same experiment is repeated again and again, the observed frequencies approach the probabilities predicted by quantum theory with remarkable precision. The problem is not that physicists do not know how to use the rule. The problem is understanding what the rule means physically. Niels Bohr placed great emphasis on the fact that experiments ultimately produce definite records that can be described in ordinary classical language. A measuring device has a pointer in one position rather than several visible positions. A photographic plate contains one particular mark. A laboratory notebook contains a definite recorded value. Bohr did not provide one simple mechanical story in which a special physical process called collapse occurs at an exact location and time. His writings instead stressed the inseparability of quantum phenomena from the experimental arrangements used to define and observe them. Werner Heisenberg also wrestled with the transition between quantum possibilities and observed facts. His uncertainty principle showed that pairs of quantities such as position and momentum cannot simultaneously possess arbitrarily sharp, experimentally accessible values within quantum mechanics. But the measurement problem goes beyond uncertainty. Even if the theory perfectly predicts the range of possible outcomes and their probabilities, why does one particular outcome appear? John von Neumann gave the measurement process a more formal treatment. Suppose a particle begins in a superposition of two possible states and interacts with a measuring device. If both the particle and the apparatus are treated quantum mechanically, the Schrödinger equation does not immediately produce one definite pointer reading. Instead, the particle becomes entangled with the apparatus. One component of the quantum state contains the particle in one condition correlated with one pointer position. Another component contains the alternative condition correlated with a different pointer position. The apparatus has therefore joined the superposition. This creates what became known as the von Neumann chain. The particle becomes correlated with the detector. The detector may become correlated with a computer. The computer may become correlated with a wider laboratory. Light escaping from the apparatus may become correlated with the result. Eventually, an observer may look at the record. If every part of that sequence is treated according to ordinary quantum evolution, there appears to be no obvious place where the chain must suddenly stop. That creates an uncomfortable question. Where exactly is the measurement? Is it the first microscopic interaction? The amplification inside the detector? The creation of a permanent record? The moment information reaches the outside environment? Or something else entirely? Popular descriptions sometimes answer this by claiming that consciousness causes the wave function to collapse. Modern quantum experiments do not require such a conclusion. Automated detectors can register outcomes and store records for hours, days, or years before any person looks at them. A particle can interact with an apparatus in an empty laboratory and leave behind a stable result. Human attention is not required for the detector to function. The difficult question is therefore not whether somebody is watching. It is why a quantum description containing several possible outcomes gives rise to the definite records that observers eventually find. There is another feature that makes measurement especially interesting. An ideal measurement is repeatable. Suppose a spin measurement produces spin-up relative to a chosen axis. If the same ideal measurement is immediately repeated, quantum mechanics predicts spin-up again with certainty. The first measurement has not merely revealed a temporary random number. The system is now in a state associated with the recorded outcome. Yet before that first measurement, if the particle was prepared in an appropriate superposition, quantum theory could predict only the probabilities of the different possible results. The individual outcome remains intrinsically probabilistic in the standard formulation. One experiment might produce one result, the next identical preparation might produce another. But after thousands or millions of repetitions, the statistical pattern becomes extremely stable. This is one of the remarkable features of quantum mechanics. It can be unpredictable in individual events while being astonishingly precise in large collections of events. The practical rules are therefore clear. Prepare a state. Allow it to evolve. Choose a measurement. Calculate the probabilities. Observe one outcome. Repeat often enough, and the statistics agree with the theory. The conceptual explanation is far less settled. Why should the smooth evolution of a quantum state appear to turn into one definite result? Does the wave function genuinely collapse? Does something else happen that merely looks like collapse? Does the measuring apparatus need a special description? Or can it be treated quantum mechanically like everything else? These questions became especially uncomfortable when physicists realized that there was nothing in the basic mathematics preventing the same logic from being extended beyond tiny particles. If a microscopic quantum event can become entangled with a detector, and the detector can become entangled with something larger, then in principle a superposition can spread outward into the macroscopic world. Erwin Schrödinger decided to make that uncomfortable implication impossible to ignore. Instead of discussing a particle, a detector, and a laboratory pointer, he imagined something much harder to dismiss as merely microscopic. He imagined a cat. Erwin Schrödinger's cat is probably the most famous animal in physics, which is an impressive achievement for a creature that never actually existed. The thought experiment appeared in 1935, during a period when some of the deepest arguments about quantum mechanics were beginning to sharpen. Physicists already knew that the theory made extraordinarily accurate predictions. What they did not agree on was what those predictions said about reality itself. One of the central disputes concerned whether the quantum state represented a complete physical description of a system, or whether something deeper might exist underneath it. Schrödinger was deeply involved in these questions, and to expose what he saw as a serious conceptual problem, he imagined a situation in which quantum uncertainty was allowed to spread from something microscopic into something unmistakably macroscopic. The setup begins with a sealed box. Inside is a cat. Also inside is a radioactive nucleus, a radiation detector, and a mechanism connected to a container of poison. The arrangement is designed so that if the radioactive nucleus decays, the detector registers the event and activates the mechanism. The poison is released. The cat dies. If the nucleus does not decay, the detector remains silent. The poison stays sealed. The cat survives. The important part is the radioactive nucleus. Quantum mechanics does not, in general, assign a definite decay time to an individual unstable nucleus in advance. Instead, it gives probabilities for whether decay will occur during a particular interval. If the nucleus is described as being in a superposition of decayed and undecayed possibilities, and the entire apparatus is treated according to quantum mechanics, then the consequences begin to spread outward. The undecayed component becomes correlated with a detector that has not triggered. That detector state becomes correlated with an intact poison mechanism, and that condition becomes correlated with a living cat. Meanwhile, the decayed component becomes correlated with a triggered detector, a released poison, and a dead cat. The result is not simply a cat whose condition is unknown because the box is closed. The mathematical description appears to contain a joint quantum state with both large-scale alternatives. One branch contains the undecayed nucleus and the living cat. The other contains the decayed nucleus and the dead cat. This is the part that made the thought experiment so memorable. But Schrödinger was not proposing that biologists should begin placing cats into boxes in the hope of producing spectacular quantum demonstrations. He was doing almost the opposite. The cat was a warning. Schrödinger wanted to show how strange the standard quantum description becomes if the rules used for microscopic systems are extended without modification to macroscopic objects. If a radioactive nucleus can remain in a superposition until measurement, then what exactly counts as the measurement? The detector? The poison mechanism? The cat? The scientist opening the box? Where does the quantum description end and the definite classical world begin? The thought experiment forces that question into the open. It also exposes the danger of treating collapse as a vaguely defined process that simply happens somewhere between the microscopic system and the everyday world. If the Schrödinger equation applies to the nucleus, why should it stop applying when the nucleus interacts with the detector? And if the detector is itself made of atoms, why should those atoms suddenly obey a different set of rules? The uncomfortable conclusion is that the quantum correlations can, at least mathematically, continue spreading. This is where entanglement becomes essential. The nucleus, detector, mechanism and cat are no longer independent systems with separate descriptions. They become correlated parts of one larger quantum state. The state of the cat is tied to the state of the detector. The detector is tied to the state of the nucleus. The alternatives form one entangled structure. This is very different from an ordinary hidden cat. Imagine placing a perfectly healthy cat inside a closed box with no quantum apparatus at all. You cannot see the animal. You might not know whether it is sleeping or awake, but your ignorance does not place the cat into a coherent quantum superposition of sleeping and waking. The cat already has some ordinary physical condition. You simply do not know what it is. In Schrödinger's thought experiment, the issue is not lack of information. The issue is whether the underlying quantum state itself contains coherent alternatives involving macroscopically different outcomes. That distinction is crucial, and it leads immediately to another question. If quantum theory allows such states mathematically, why do we never see them? Why do we not encounter tables in superpositions of different locations? Why does a real cat never appear visibly alive and dead in the same coherent state? The practical answer has a great deal to do with isolation. A living organism is about as badly isolated as a quantum system can be. It is warm. It contains an enormous number of particles. Its molecules are constantly colliding, vibrating, reacting and exchanging energy. It emits thermal radiation. It interacts with surrounding air. photons scatter from its surface. Its internal chemistry produces vast numbers of correlations every moment. Even inside a sealed box, the cat is surrounded by an environment, and in practice, that environment would become entangled with the different macroscopic alternatives almost immediately. Information about whether the cat is alive or dead would leak into countless degrees of freedom. A molecule might scatter differently. A photon might be emitted differently. The distribution of heat would differ. The motion of air would differ. The microscopic details of the box would become correlated with the outcome. Maintaining coherent interference between two such enormous alternatives would be fantastically difficult. But this practical difficulty does not completely remove the theoretical question. Suppose the fundamental quantum equations apply universally. If there is no confirmed law saying that sufficiently large objects must stop obeying them, then what exactly prevents macroscopic superpositions from existing in principle? Perhaps nothing does. Perhaps they form but become impossible to observe because coherence is lost extraordinarily quickly. Perhaps the wave function really does collapse through some physical mechanism. Perhaps all branches continue in some larger description. Different interpretations answer the question differently. What Schrödinger achieved was to make it impossible to ignore. His cat took a microscopic quantum problem and enlarged it until the conceptual tension became obvious. The puzzle was no longer just about an electron, an atom, or a radioactive nucleus. It was about the boundary between quantum possibility and the definite world around us, and the route toward understanding why that boundary appears so convincing begins with the process that quietly spreads quantum information into the environment. Entanglement. Entanglement is one of the features of quantum mechanics that sounds almost designed to make the theory more mysterious than necessary. But at its core, the idea is quite precise. Two or more quantum systems are entangled when their combined state cannot be completely described by assigning each part its own independent quantum state. Instead, the most complete description belongs to the system as a whole. The parts are linked through correlations that are built into the joint quantum state. This becomes especially important when superposition spreads beyond a single particle. Imagine two particles interacting and becoming correlated so that one possible component of the state contains one arrangement, while another component contains a different arrangement. The combined system can then exist in a superposition of those correlated alternatives. Neither particle on its own carries a complete description of the whole situation. The information is shared across the joint state. This distinction between superposition and entanglement is important. Superposition describes a quantum state as a coherent combination of alternatives. Entanglement describes a special kind of combined quantum state, in which the alternatives involve correlations between different systems. A single particle can be in a superposition without being entangled with anything else, but once several systems become involved, superposition can generate entangled states in which the parts can no longer be treated independently. This issue became central to one of the most famous arguments in the history of quantum physics. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper challenging the idea that quantum mechanics provided a complete description of physical reality. Their argument considered two systems that had interacted and then moved apart. Quantum mechanics allowed the two systems to remain strongly correlated even after their separation. Einstein and his colleagues found this deeply troubling. They believed that physical properties should exist locally, and that what happened to one distant object should not instantly determine the physical reality of another separated object. Their paper suggested that quantum mechanics might therefore be incomplete, perhaps because some deeper set of hidden variables determined the outcomes in advance. The same year, Erwin Schrödinger responded to these discussions and introduced the term entanglement. He recognized that this feature was not a minor curiosity. It was one of the defining differences between quantum mechanics and classical physics. For several decades, the debate remained partly philosophical. Then John Stuart Bell found a way to turn it into an experimental question. In 1964, Bell showed that a broad class of theories based on local hidden variables could not reproduce all of the correlations predicted by quantum mechanics. His result became known as Bell's theorem. The importance of Bell's work was that it created experimentally testable inequalities. If nature followed a local hidden variable picture of the kind Einstein had hoped might underlie quantum mechanics, certain statistical limits should never be exceeded. Quantum mechanics predicted that entangled particles could violate those limits. Experiments followed. In the early 1980s, Alain Aspect and his collaborators performed influential tests using pairs of entangled photons. Their results agreed with the quantum predictions and violated the constraints expected from local hidden variable theories. Later experiments improved the technology, increased the separation between measurements, and closed important experimental loopholes. By the middle of the 21st century, several so-called loophole-free Bell tests had produced results consistent with quantum mechanics. The conclusion is not that information can be freely transmitted faster than light. Individual measurement results remain random. What the experiments show is that the correlations between entangled systems cannot be explained by a simple model in which each particle carries a hidden local instruction list determining every outcome in advance. Entanglement is therefore not merely a mathematical curiosity. It produces measurable relationships that classical local descriptions cannot reproduce. And it brings us directly back to Schrödinger's cat. The cat is often described casually as being alive and dead at the same time. But the more accurate quantum description involves entanglement. The radioactive nucleus, detector, mechanism and cat become correlated. One component of the joint state contains the undecayed nucleus, the silent detector, the untouched mechanism, and the living cat. Another contains the decayed nucleus, the activated detector, the released poison, and the dead cat. These are not independent possibilities belonging separately to each object. They form one entangled quantum state. And in a real environment, the chain would not stop with the cat. Air molecules would collide differently with the two alternatives. Thermal photons would be emitted differently. Light scattering from the box would carry information about its internal condition. Vibrations in the surrounding material could become correlated with the outcome. Very quickly, the environment itself would become entangled with the alternatives. This is where the connection to decoherence begins. Suppose a quantum system is in a superposition of two alternatives. If nothing outside the system becomes correlated with which alternative is present, the phase relationship between them can remain accessible. The alternatives can later be recombined and made to interfere. But if the surrounding environment becomes entangled with them, information about the alternatives spreads outward. One environmental state becomes correlated with one component. A different environmental state becomes correlated with the other. The phase information has not necessarily vanished from the complete quantum description. Instead, it has become distributed through a much larger entangled system. From the perspective of someone measuring only the original particle, the coherence becomes increasingly inaccessible. Interference fades. This is a subtle but important distinction. It is tempting to say that entanglement with the environment simply destroys the quantum state. That is not quite what standard quantum theory says. If the entire system and environment are treated together, their combined state can continue evolving quantum mechanically. The coherence may still exist globally in correlations spread throughout that enormous state. The problem is that recovering it would require controlling all of those environmental degrees of freedom with extraordinary precision. For a small laboratory system, this can sometimes be attempted. For a macroscopic object interacting with trillions upon trillions of particles, it rapidly becomes hopeless. So the quantum information has not necessarily been erased, it has become dispersed. From the viewpoint of the small subsystem we can actually observe, the alternatives no longer interfere in any useful way. This is why entanglement plays two apparently opposite roles in modern physics. When uncontrolled, entanglement with the environment causes coherence to become inaccessible and drives decoherence. When carefully engineered, entanglement becomes one of the most valuable resources in quantum information science. Quantum computers deliberately create entangled states because their correlations can perform tasks that collections of independent quantum bits cannot reproduce in the same way. The same phenomenon that makes macroscopic superpositions so difficult to observe can therefore become useful when it is created selectively and protected carefully. Entanglement connects the microscopic system to everything it touches, and in the everyday world, everything touches something. That simple fact is one of the main reasons the fragile interference of quantum alternatives disappears so quickly from view. The everyday world feels stable because quantum alternatives rarely remain isolated for long. A dust grain seems to occupy one place. A chair has one position. A cup sits on the table rather than appearing as a visible blur of mutually exclusive possibilities. Quantum mechanics does not simply stop applying to these objects. Instead, something else happens. Their quantum states become entangled with the environment so rapidly that the delicate phase relationships required for interference become effectively impossible to observe. This process is called decoherence. The foundations of environmental decoherence were developed in important work by Heinz Dieter Zeh beginning in the 20th century. Zeh argued that the interaction between a quantum system and its surroundings could explain why superpositions that are perfectly acceptable in the microscopic theory seem to disappear from ordinary experience. Wojciech Zurek later developed this framework much further, showing in detail how environmental interactions can select stable states and produce the appearance of a classical world from underlying quantum dynamics. The word environment sounds as though it refers only to the air outside a laboratory. In quantum physics, it means much more than that. The environment includes anything that is not being kept under careful control as part of the system. Gas molecules can be part of the environment, so can photons, thermal radiation, electromagnetic fields, mechanical vibrations, nearby atoms, and even internal degrees of freedom within a large object can effectively behave as an environment for the small part we are trying to observe. Suppose a particle is prepared in a coherent superposition of two positions. If the particle could remain perfectly isolated, the two components could retain a definite relative phase. They might later be recombined and made to interfere. But now imagine that a photon scatters from the particle. If the photon interacts differently depending on which position the particle occupies, the outgoing photon can carry information about the alternatives. One state of the photon becomes correlated with one position. A different photon state becomes correlated with the other. The particle and photon are now entangled. Add another photon, and the correlation spread further. Then an air molecule collides with the system. Then another. Then thermal radiation leaves the object. Very quickly, information about the original alternatives becomes distributed across a vast number of environmental states. The phase relationship has not necessarily been deleted from the complete quantum description. Instead, it has become hidden inside an enormous web of correlations. From the point of view of someone measuring only the original system, the interference becomes inaccessible. This is the heart of decoherence. A useful way to describe this mathematically is with a reduced density matrix. The full density matrix can describe the combined state of the system and its environment, but in practice, we almost never track every environmental molecule, photon, vibration, and electromagnetic mode. Instead, we ignore the details we cannot control and calculate a reduced description for the system alone. When decoherence has acted strongly, the terms associated with coherent interference between alternatives become extremely small in this reduced description. The system begins to behave almost as though it were an ordinary classical statistical mixture. That does not necessarily mean the complete quantum state has collapsed. It means the coherence is no longer locally accessible. This distinction is important. Decoherence explains why interference disappears from ordinary observation. It explains why alternative macroscopic states stop behaving like coherent possibilities that can later be recombined. But decoherence alone does not tell us why one unique outcome is experienced. If the full system and environment continue to evolve according to the Schrödinger equation, the combined quantum state can still contain multiple correlated alternatives. So decoherence addresses a major part of the measurement problem, but it does not automatically solve every interpretive question surrounding collapse and definite outcomes. Another key idea developed in this framework is the pointer basis. Not every possible superposition is equally stable when a system interacts with its environment. Certain states survive environmental monitoring better than others. For many macroscopic objects, approximate position states are especially robust. The environment is constantly gathering information about where things are. Photons bounce from surfaces, air molecules collide with objects. Heat is exchanged. These interactions tend to preserve relatively well-defined locations while rapidly destroying coherent superpositions of very different locations. Wojciech described this process using the idea of environment-induced superselection, often shortened to einselection. The environment effectively favors certain stable states over fragile superpositions. These favored states are not chosen by conscious observers. They emerge from the structure of the physical interactions. This helps explain why the classical world seems filled with objects that possess definite positions. The environment continuously monitors location-like properties, and the larger the object, the more opportunities there are for information about its position to leak outward. For a macroscopic object in ordinary conditions, this happens with extraordinary speed. An enormous number of photons can scatter from it. Air molecules strike its surface continuously. Thermal radiation carries information away. Each interaction creates new correlations. The surroundings quickly become full of redundant records about where the object is and what it is doing. This is one reason a large object can appear so decisively classical. Its state is not merely interacting with one detector. It is being monitored by the universe around it. There is a simple analogy that can help, although it must be treated carefully. Imagine placing a small amount of cream into a cup of coffee. At first, the cream is concentrated in one place. As you stir, it spreads into increasingly complicated patterns. Eventually, it becomes so thoroughly mixed that reconstructing the original drop would be practically impossible. The information has not necessarily vanished from the fundamental motions of every molecule. It has become dispersed into an enormous number of microscopic details. Decoherence is similar in the sense that quantum phase information spreads into the environment, but unlike cream, coherence is not a visible substance. What spreads are correlations and phase relationships in the quantum state. In principle, fundamental quantum evolution can remain reversible. In practice, reversing decoherence would require gaining precise control over every environmental degree of freedom carrying information about the original alternatives. For even modest macroscopic systems, that demand becomes absurdly difficult. You would need to reverse countless photon scatterings, molecular collisions, vibrations, and thermal exchanges with extraordinary precision. So although the underlying equations may permit reversibility, the process becomes effectively irreversible in the real world. This is the bridge between quantum and classical behavior. Microscopic systems can display superposition when they are isolated carefully enough. Macroscopic systems interact constantly with their surroundings. Those interactions distribute coherence into the environment so rapidly that interference between large-scale alternatives becomes essentially invisible. The quantum rules have not disappeared. They have become hidden beneath an overwhelming network of entanglement. And that is why the stable classical world around us can emerge from a theory built on superposition. One of the easiest mistakes to make with quantum mechanics is to imagine that it belongs only to very small things. Electrons behave quantum mechanically, atoms behave quantum mechanically, molecules can behave quantum mechanically. But somewhere, perhaps at the size of a grain of dust or a cat or a person, the rules must surely change. That sounds reasonable, but it is not how modern quantum theory is usually understood. There is no confirmed size at which quantum mechanics simply switches off. Large objects are still made from quantum particles, and the laws governing those particles do not suddenly vanish when enough of them are assembled together. The real problem is not size by itself. The problem is preserving coherence. A macroscopic object contains an enormous number of particles. Even something as small as a grain of dust can contain billions upon billions of atoms, depending on its size and composition. Each atom has internal degrees of freedom. The atoms vibrate. They collide. Electrons interact. Molecules rotate. Energy shifts between different parts of the object. All of this internal activity creates opportunities for quantum information to spread, and the object is not isolated from the outside world either. At ordinary temperatures, matter constantly exchanges thermal radiation with its surroundings. Warm objects emit infrared photons. They also absorb radiation arriving from elsewhere. Those photons carry information. A photon scattered from an object can, in principle, become correlated with its position, orientation, shape, or temperature. If two components of a superposition correspond to meaningfully different physical arrangements, then the outgoing radiation can help distinguish between them. That distinction is enough to damage coherence. Air creates another problem. At normal atmospheric pressure, exposed objects are struck by enormous numbers of gas molecules every second. Each collision is tiny. But there are so many of them that the surrounding air effectively performs continuous environmental monitoring. If an object were somehow placed in a spatial superposition, with one component here and another component some distance away, collisions with surrounding gas molecules could carry information about which location was involved. The larger the separation between those alternatives, the easier they usually are for the environment to distinguish. That means large spatial superpositions can decohere especially quickly. A superposition in which two positions differ by an atomic scale distance may be difficult for the environment to resolve. Separate those same alternatives by millimeters or centimeters. and surrounding photons or molecules can distinguish them far more easily. The environment does not need to understand what it has discovered. It simply needs to become correlated differently with the two possibilities. Light also performs this role constantly. Every visible object you can see is visible, because photons have interacted with it and reached your eyes. But those photons do not wait for a conscious observer before carrying information away. They scatter into walls, furniture, air, cameras, and the wider environment. Thermal photons do much the same thing at wavelengths our eyes cannot detect. As a result, ordinary objects leave an enormous number of environmental records. Their positions become copied into the surrounding world again and again. This is one reason macroscopic reality appears so stable. The environment is continually recording it. There is another scale problem as well. Every moving object has a de Broglie wavelength. That includes electrons, it includes atoms, and in principle it includes footballs, coffee cups, people and planets. But the wavelength depends inversely on momentum. For an ordinary object with everyday mass and speed, the de Broglie wavelength is fantastically small. So small, in fact, that arranging an interference experiment capable of resolving it becomes extraordinarily difficult. This does not mean the object has ceased to be quantum mechanical. It means the wave-like signatures become inaccessible under ordinary conditions. Size therefore works against observable superposition in several ways at once. Larger objects tend to have shorter de Broglie wavelengths. They interact with more particles. They scatter more radiation. They possess more internal degrees of freedom. And they are generally much harder to isolate. A warm living organism pushes all of these problems to an extreme. A cat is constantly exchanging heat with its surroundings. Its molecules are undergoing chemical reactions. Its cells are moving ions and water. Blood flows. Proteins vibrate. Electrical signals travel through nerves. The animal emits thermal radiation and interacts continuously with the air. Even if nobody opens the box, this internal and external activity is already enough to create an immense web of environmental correlations. A human observer adds very little to the basic problem. The cat does not need somebody looking at it in order to behave classically. Its own body and surroundings are already doing an impressive amount of monitoring. This helps explain how stable classical trajectories emerge. Macroscopic objects are not perfectly classical underneath. Instead, certain narrow quantum states become much more robust than widely separated coherent superpositions. Environmental interactions repeatedly favor states with reasonably well-defined positions and motions. Those states evolve in ways that closely resemble the trajectories predicted by classical physics. A thrown ball follows a smooth path. A planet follows an orbit. A cup remains on the table. Strictly speaking, the classical picture is approximate, but it is such an overwhelmingly successful approximation that the underlying quantum character becomes almost impossible to notice. This is why laboratory demonstrations of larger superpositions demand such extreme conditions. Scientists remove air using high vacuum systems. They lower temperatures to reduce thermal motion and radiation. They shield experiments from unwanted electromagnetic fields. They isolate equipment from vibrations. They control the timing of interactions with extraordinary precision. Sometimes, even a tiny amount of stray heat or an unnoticed collision is enough to destroy the effect they are trying to preserve. The laboratory is not forcing quantum mechanics to exist. Quantum mechanics is already there. The laboratory is simply preventing the environment from hiding it. This is the key difference. Everyday objects do not look classical because they have somehow escaped quantum physics. They look classical because their quantum coherence is dispersed almost immediately into the enormous world around them. The superposition principle has not failed. It has become practically impossible to reveal, and that is why the strange behaviour seen so clearly in carefully isolated particles almost completely disappears when we look at the ordinary objects surrounding us. If large objects remain quantum systems in principle, then a natural experimental challenge appears. How large can a superposition become before it becomes impossible to preserve? There are several ways to make that question more demanding. Scientists can increase the mass of the object. They can increase the number of particles it contains. They can increase the physical distance between the alternatives. Or they can make the internal structure of the object more complicated. Each step makes isolation harder because a larger or more complex system usually provides more opportunities for the environment to discover which alternative is present. That discovery is exactly what experimenters try to prevent. One of the most striking approaches has involved matter-wave interference with large molecules. Marcus Arndt, Anton Zeilinger, and their collaborators demonstrated interference using fullerene molecules, including carbon-60, a nearly spherical molecule built from 60 carbon atoms. These molecules are enormous compared with an electron. They have internal vibrations, rotations, and many interacting particles. And yet, under carefully controlled conditions, their centre of mass motion can still display quantum interference. Later experiments pushed the idea further, with even larger organic molecules containing hundreds of atoms. The importance is not that these molecules are anywhere close to everyday objects in size. They are still microscopic. But they are sufficiently complex to make a powerful point. Quantum behaviour does not suddenly disappear just because a system contains many particles. There is no obvious cliff where nature announces that the object has become too complicated and must now behave classically. Instead, coherence becomes progressively harder to preserve. Molecular interference experiments require extraordinary control. The molecules are often sent through regions of very high vacuum so that collisions with stray gas particles become rare. Their trajectories must be prepared carefully. The gratings or optical fields used to split and recombine the quantum paths must be controlled with extreme precision. Thermal emission also matters. A sufficiently warm molecule can emit photons, and those photons may carry information about which path the molecule followed. So even the object's own heat can reveal the alternative and weaken the interference. The experiment is therefore a quiet battle against information leakage. Different laboratories approach the same basic problem using very different physical systems. Serge Hiroke and his collaborators explored superposition in the electromagnetic field itself. Using cavity quantum electrodynamics, they trapped microwave fields between highly reflective mirrors and allowed carefully prepared atoms to interact with them. In these experiments, researchers could create and probe superpositions of distinct electromagnetic field states. Some of these are often described as Schrödinger cat states because they contain two distinguishable alternatives combined coherently within one quantum state. They are not cats, of course. No whiskers are involved. But mathematically, they capture the same basic idea of macroscopically distinguishable, or at least mesoscopically distinct alternatives existing within a coherent state. Hiroshi's work also allowed researchers to watch decoherence occur. As information leaked into the environment, the interference associated with the cat-like state faded. Rather than discussing the quantum to classical transition only in abstract terms, physicists could observe the gradual loss of coherence directly. David Wineland and his collaborators pursued another route using trapped ions. Charged atoms can be confined with carefully controlled electromagnetic fields and cooled until their motion becomes highly quantum mechanical. The internal electronic state of an ion can then be linked with its vibrational motion. This allows researchers to prepare superpositions in which different internal states are correlated with different motional states. The system can be manipulated with laser pulses, recombined, and measured with remarkable precision. These experiments helped establish many of the techniques later used in quantum information processing. Superconducting quantum circuits provide another striking example. These devices contain enormous numbers of electrons moving collectively through engineered electrical circuits. At sufficiently low temperatures, superconductivity allows electrical currents to flow with exceptionally little resistance, and certain circuit variables can behave as quantum degrees of freedom. Researchers have created superpositions associated with different current directions or different magnetic flux configurations. These states involve collective behavior across a device that is vastly larger than an atom. That does not mean every electron in the circuit is literally occupying two widely separated positions. The quantum variable belongs to a collective electrical state. This distinction is important because the phrase macroscopic superposition can refer to several different ideas. A many particle system may display coherent quantum behavior without every microscopic constituent being placed into two completely separated spatial arrangements. Even so, superconducting circuits show that quantum coherence can survive in engineered systems involving an enormous number of particles. Keeping them coherent requires extreme conditions. Many superconducting quantum devices operate at temperatures only a tiny fraction of a degree above absolute zero. The purpose is to suppress thermal excitations that would disturb the quantum state. Experiments are also shielded from electromagnetic noise, vibrations, stray radiation, and other disturbances that can reveal or alter the system. A further frontier involves optomechanics. Here, scientists attempt to control the motion of small mechanical objects using light. These objects can include tiny resonators, membranes, suspended structures, or levitated particles containing vast numbers of atoms. The goal is to cool their motion close to the quantum ground state and then prepare states that reveal genuinely non-classical behavior. Creating a convincing spatial superposition of an increasingly massive object would be especially significant. But proving that such a state exists requires more than showing that the object has an uncertain position. Ordinary uncertainty is not enough. Coherence has to be demonstrated. Researchers therefore look for interference revival, phase-sensitive measurements, parity signals, state tomography, or other signatures showing that the alternatives retain a quantum relationship. State tomography reconstructs information about a quantum state from many different measurements. Parity measurements can reveal features of the state that distinguish coherent superpositions from ordinary mixtures. Interference revival can show that phase information has been preserved and later recombined. These methods are essential because an uncertain outcome alone does not prove superposition. A classical object can be uncertain too. What matters is whether the alternatives can still interfere. As experiments move toward heavier, more complex, and more widely separated systems, they also begin to test deeper questions. Standard quantum mechanics does not specify a known maximum size for superposition, but some proposed modifications to quantum theory suggest that sufficiently large systems might collapse spontaneously. Other ideas suggest that gravity could somehow play a role when distinct mass distributions are placed in superposition. These possibilities remain unconfirmed. That is why larger superposition experiments are scientifically valuable even when no new physics appears. Every successful experiment pushes the tested domain of quantum mechanics a little farther. The pattern so far is remarkably consistent. Make the system larger, and preserving coherence becomes harder. Improve the isolation, cooling, shielding, and control, and quantum behavior can reappear. Nature has not yet revealed a simple boundary where superposition stops being allowed. The challenge has been keeping the environment quiet enough to let us see it. Quantum mechanics is extraordinarily good at telling us what we are likely to observe. It is much less settled on the question of what, exactly, exists before we observe it. This distinction has followed the theory almost from the beginning. Physicists can agree on the mathematical rules used to calculate probabilities, predict interference patterns, design experiments, and build working technologies. Yet they can disagree sharply about what the wave function itself represents. Is it a real physical object? Is it information? Is it a description of relationships between systems? Does it collapse? Does it branch? Does it guide hidden particles? Or does it simply encode what an observer should expect to experience? These questions belong to the interpretation of quantum mechanics. One of the oldest families of interpretations is usually grouped under the broad name Copenhagen interpretation. Niels Bohr and Werner Heisenberg are closely associated with it, although there was never one perfectly uniform Copenhagen doctrine accepted in exactly the same way by every early quantum physicist. Bohr placed particular emphasis on measurement arrangements and complementarity. The properties we can meaningfully discuss depend on how an experiment is arranged, and the outcome appears as a definite classical record. Heisenberg often described quantum states in terms of possibilities that become actualized through measurement. In traditional textbook versions influenced by these ideas, the wave function evolves according to quantum mechanics until a measurement takes place, at which point one outcome is selected. This works operationally. But it leaves open the question of what collapse physically is. A radically different approach was introduced by Hugh Everett III in the 1950s. Everett proposed what he called the relative state formulation. In this picture, there is no special physical collapse of the universal wave function. Quantum evolution continues according to the same rules at all scales. When a measurement occurs, the system, measuring device, environment, and observer become entangled. Different outcomes remain represented in different branches of the total quantum state. This idea later became closely associated with the many worlds interpretation. The phrase many worlds can make it sound as though universes are constantly popping into existence like soap bubbles. The underlying proposal is more precise. The universal wave function contains different correlated branches, and decoherence prevents those branches from producing ordinary observable interference with one another. An observer within one branch experiences one definite outcome. Another approach is David Bohm's pilot wave theory. Here, particles possess definite configurations, such as definite positions, while a wave function evolves alongside them and guides their motion. The wave function can contain several branches, but the actual particle configuration occupies one particular branch in an effective sense. Bohmian mechanics therefore keeps something resembling definite particle trajectories while retaining the quantum wave function. However, the theory is explicitly non-local. The behavior of one part of an entangled system can depend on the configuration of distant parts in ways that cannot be reduced to a purely local classical mechanism. Other physicists have taken a very different route and suggested that wave function collapse might be a real physical process. Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber developed one influential objective collapse model. Their idea introduced rare spontaneous collapses into quantum dynamics. For a single microscopic particle, these collapses would occur so infrequently that ordinary quantum predictions would remain almost unchanged. But in a large system containing enormous numbers of particles, the effect would accumulate. Macroscopic superpositions would therefore become unstable automatically. This is appealing because it attempts to explain why tables and cats appear definite without placing measurement in a special category. But it also changes the underlying dynamics of quantum mechanics, meaning that sufficiently sensitive experiments could potentially detect deviations from the standard theory. Roger Penrose has suggested another possibility. He has argued that gravity may somehow be connected with the reduction of quantum superpositions involving significantly different mass distributions. The basic intuition is that placing mass into two different configurations also places the associated gravitational field into an unusual situation. Penrose has proposed that such states may be fundamentally unstable. This remains speculative. There is currently no established experimental evidence showing that gravity causes wave function collapse in this way. Other interpretations attempt to preserve the standard equations while changing the meaning assigned to the quantum state. Carlo Rovelli's relational interpretation argues that physical properties need not exist as absolute values independent of every interaction. Instead, a property can be definite relative to one physical system while being described differently relative to another. The emphasis shifts away from demanding one universal set of properties possessed by everything at once. Quantum Bayesianism takes another approach. Associated particularly with Christopher Fuchs, Erdős Schack and Carlton Caves, it treats the quantum state as expressing an agent's structured expectations about future experiences. On this view, the wave function is not necessarily a physical object spread through the world. It is a tool for assigning probabilities to possible outcomes based on an agent's information and expectations. These interpretations therefore differ in very deep ways. Some add new physical dynamics. Objective collapse theories modify quantum evolution itself. Some add additional physical variables. Bohmian mechanics introduces definite particle configurations alongside the wave function. Others, including many worlds, relational quantum mechanics, and quantum Bayesianism, largely preserve the standard formalism while interpreting its meaning differently. And this creates an unusual situation. Several interpretations can make the same experimental predictions across the domains where ordinary quantum mechanics has been tested. If two interpretations predict exactly the same measurable results, then no experiment can distinguish between them within that shared domain. That is why no single interpretation currently enjoys decisive experimental confirmation over all major rivals that reproduce standard quantum mechanics. The disagreement is not simply the result of physicists failing to perform enough measurements. In some cases, the competing pictures are constructed to reproduce the same measurable statistics, but this does not mean interpretation can never meet experiment. Objective collapse models can predict tiny deviations from ordinary quantum theory. Experiments involving increasingly massive superpositions can search for such effects. Future tests may also explore whether gravity behaves in an unexpected way when significant masses are placed into quantum superpositions. If any reproducible deviation from standard quantum mechanics appeared, some interpretive possibilities could become genuine competing physical theories with experimentally distinguishable predictions. For now, superposition occupies a fascinating position. Its measurable consequences are among the most reliable features of modern physics. Interference can be predicted. quantum states can be prepared. Relative phases can be controlled. Superpositions can be destroyed and restored. What remains unsettled is what those successful calculations are telling us about reality itself. Fortunately, technology does not have to wait for philosophy to finish. Engineers can manipulate quantum superpositions, even while physicists continue debating what the wave function ultimately means. And perhaps nowhere is that more obvious than in the quantum computer. There, superposition stops being only a conceptual puzzle. It becomes something that must be created, controlled, protected, and made useful. A classical computer stores information using bits. At the simplest level, a bit represents one of two distinguishable logical values. We usually call them 0 and 1. The physical device underneath may be a transistor, a voltage level, a magnetic region, or some other system engineered so that two conditions can be reliably distinguished. At any particular moment, an ordinary classical bit is treated as having one value or the other. A quantum bit begins with the same idea of two distinguishable states, but then quantum mechanics adds something that classical information does not possess. A quantum bit, usually called a qubit, can occupy a coherent superposition of its two computational basis states. One basis state corresponds to 0, the other corresponds to 1. But before measurement, the quantum state can contain probability amplitudes associated with both. Those amplitudes have magnitudes and a relative phase, which means the state contains more structure than simply saying there is some probability of finding 0 and some probability of finding 1. The coherence between the alternatives allows them to interfere, and that is what eventually makes the quantum bit useful. There is no single physical object that must serve as a quantum bit. One laboratory might use the spin of an electron, another might use different internal energy states of a trapped ion. Photons can encode quantum information in polarization or other properties. Neutral atoms can be confined and manipulated with precisely controlled laser fields. Superconducting electrical circuits can also behave as engineered two-level quantum systems when cooled to extremely low temperatures. These devices can look completely different from one another, but the logical idea is the same. Two quantum states are selected as the computational basis, and scientists learn how to prepare, manipulate, protect, and measure coherent combinations of them. The motivation for doing this emerged partly from a problem that quantum physics itself created. Classical computers can simulate quantum systems, but the mathematical resources required can grow extremely quickly as the number of interacting quantum components increases. Richard Phillips Feynman argued in the early 1980s that perhaps the most natural machine for simulating nature would be a machine that itself followed quantum rules. Instead of forcing a classical computer to keep track of an enormous quantum state indirectly, one might build a controllable quantum system and allow its own physical evolution to perform part of the calculation. David Deutsch later developed the concept of a universal quantum computer, helping establish quantum computation as a general model of information processing rather than merely a specialized simulator. But building such a machine means persuading quantum systems to behave in an unusually disciplined way. A quantum bit must first be prepared in a known state. Depending on the technology, this might involve extreme cooling, optical pumping with lasers, microwave radiation, magnetic fields, or carefully timed electromagnetic interactions. Once prepared, the state can be manipulated using quantum gates. A quantum gate is not quite like a classical switch. An ordinary logic operation might change one definite pattern of bits into another. An ideal quantum gate transforms probability amplitudes and relative phases while preserving the coherence of the state. The underlying operations are reversible in the mathematical sense used by quantum mechanics. This allows information encoded in amplitudes to be rearranged and later made to interfere. One particularly common operation is called the Hadamard operation. Applied to one of the computational basis states, it can create a balanced superposition in which the two possible measurement outcomes have equal amplitude magnitude. If the quantum bit began in the state associated with 0, the operation can place it into a coherent combination of 0 and 1. That does not mean a measurement will reveal both answers. Measure immediately, and only one classical result appears. Repeated measurements of identically prepared systems give 0 on some runs and 1 on others, with probabilities determined by the state. The power lies in what can happen before measurement. With several quantum bits, the mathematical space of possible states grows extremely quickly. 2 quantum bits require amplitudes associated with 4 computational configurations. 3 require 8. 10 require 1024. Add more quantum bits, and the number of amplitudes doubles each time. This exponential growth is one reason quantum computation is so intriguing. A sufficiently large quantum register can occupy a state involving an enormous collection of computational configurations. But this point is also responsible for one of the most persistent misconceptions about quantum computers. A quantum computer does not simply calculate every possible answer and then hand all of them to us. Measurement does not reveal the entire quantum state. When the register is measured, the result is an ordinary classical outcome drawn according to the final probability distribution. Most of the detailed amplitude information is no longer directly accessible. So merely creating a huge superposition accomplishes very little by itself. The amplitudes have to be manipulated intelligently before measurement. That requires exceptionally precise control. Researchers care about coherence time, meaning how long useful quantum information can survive before environmental interactions degrade it. They care about gate fidelity, which describes how closely a real operation matches the intended quantum transformation. They care about readout accuracy, because even a perfectly prepared state is of little use if the final measurement is frequently misidentified. And they care constantly about isolation. A stray photon, an unwanted electrical fluctuation, thermal motion, material defects, or coupling to another part of the device can leak information into the environment. That leakage produces decoherence. The very process that explains why large objects appear classical is therefore one of the main enemies of quantum computation. Research groups around the world approach this problem using different technologies. The National Institute of Standards and Technology has carried out extensive work with trapped ions and precision quantum control. International Business Machines has developed superconducting quantum processors. Google Quantum Artificial Intelligence has pursued superconducting devices and quantum error correction research. Universities and national laboratories work with neutral atoms, photons, semiconductor spins, ions, superconducting circuits, and other platforms. No single architecture has yet made every engineering problem disappear. Each has its own advantages and difficulties. Some quantum bits can preserve coherence for relatively long periods, but are slower to manipulate. Others can perform operations rapidly, but may be more vulnerable to noise. Some are easier to manufacture at scale. Others offer exceptionally precise measurements. The central challenge is always a delicate balance between control and isolation. The system must be protected from the outside world, yet researchers must still interact with it strongly enough to perform operations and eventually measure the answer. A perfectly isolated quantum computer would preserve its quantum state rather well. Unfortunately, it would also be rather difficult to ask it to do anything. Superposition therefore provides the space in which quantum computation operates, but it is not the computation by itself. The important step is learning how to control the amplitudes and phases inside that superposition. A useful quantum algorithm must arrange those possibilities so that some reinforce one another while others cancel. In that sense, the quantum computer does not win by simply holding many possibilities. It wins when it can by teaching those possibilities how to interfere. Quantum computing becomes much easier to misunderstand if superposition is described as though it was simply an enormous collection of calculations happening independently at the same time. The usual story sounds wonderfully powerful. A classical computer tries one possibility after another, while a quantum computer places every possible answer into superposition, checks them all simultaneously, and then reads out the correct one. Unfortunately, nature has included a rather important catch. When a quantum system is measured, we do not receive a neat list of every amplitude inside its state. We receive a classical result. If a quantum computer merely created a gigantic superposition of possible answers and immediately measured it, the result would generally be little better than drawing one possibility from a hat. The real power of quantum computation comes from what happens before measurement. A quantum algorithm prepares amplitudes across many computational configurations and then manipulates them through carefully chosen quantum gates. Those gates alter amplitudes and relative phases. The different components of the state can then interfere. Some possibilities reinforce one another. Others cancel. A useful algorithm arranges this interference so that desirable outcomes become more likely to appear when the final measurement is made. So superposition provides the possibilities. Interference performs much of the useful sorting. Without interference, merely possessing an enormous quantum state would not automatically solve anything. This distinction can be seen clearly in one of the most famous quantum algorithms. In 1994, Peter Williston Shaw developed a quantum algorithm for finding the prime factors of large integers. Factoring is easy to describe. Take a whole number that was created by multiplying two large prime numbers and determine which primes were used. For small numbers, this is simple. As the numbers become extremely large, the task becomes much more demanding for the best known classical factoring methods. Shaw's algorithm does not simply try every possible factor and somehow inspect all of them at once. Its central quantum component is designed to uncover a hidden periodic structure within a related mathematical problem. The quantum state is prepared across many possible values. Their phases evolve in a controlled way. A quantum Fourier transform then uses interference to make information about the relevant period much more likely to appear in the measured result. Classical processing takes that information and uses it to recover the factors. For sufficiently large, fault-tolerant quantum computers, Shaw's algorithm would offer a dramatic theoretical advantage over known classical factoring algorithms. That possibility is one reason quantum computing attracted so much attention. But it is not representative of every computational problem. Another important example came from Love Kumar Grover in 1996. Grover developed a quantum search algorithm for finding a desired item within an unstructured collection of possibilities. If a classical method has no helpful structure to exploit, it may need to inspect a number of possibilities proportional to the size of the collection. Grover's algorithm reduces the required number of searches to roughly the square root of that size. That is a meaningful improvement, but it is not an unlimited one. A collection containing 1 million possibilities does not suddenly become a one-step problem. The quantum advantage is approximately a reduction from around 1 million checks to around 1,000 idealized search steps. The underlying trick is again interference. The algorithm alters the phase associated with the desired answer and repeatedly transforms the quantum state so that amplitude moves toward that answer. After enough repetitions, measuring the system has a high probability of revealing the desired result. The quantum computer does not open a magical window onto every possibility. It reshapes a probability distribution. Entanglement becomes important when many quantum bits are involved. A collection of independent quantum bits can each occupy superpositions, but the total state may still be relatively simple if every quantum bit can be described separately. Entangled quantum bits are different. Their state contains correlations that cannot be reduced to independent descriptions of each part. This gives quantum processors access to complex multi-part states that are central to many algorithms, simulations, and error correction schemes. But greater complexity also creates greater vulnerability. Quantum information cannot simply be protected by copying it repeatedly in the ordinary classical way. The no-cloning theorem states that an arbitrary unknown quantum state cannot be copied perfectly. This is not merely an engineering inconvenience, it follows from the mathematical structure of quantum mechanics. A classical computer can protect a bit by making several identical copies and comparing them later. Quantum systems require a more subtle strategy. That strategy is quantum error correction. Instead of copying an unknown quantum state directly, information representing one logical quantum bit can be distributed across an entangled collection of physical quantum bits. Carefully designed measurements then reveal information about errors without directly revealing the protected logical quantum state itself. These measurements produce error syndromes. They can indicate that a particular type of error has occurred while leaving the encoded quantum information intact. This allows certain disturbances to be detected and corrected before they accumulate beyond recovery. The principle is elegant. The engineering is difficult. Real quantum bits suffer from many forms of noise. Their phases drift. Unwanted interactions occur between neighboring components. Control pulses are imperfect. Measurements can be misidentified. Materials contain defects. Thermal excitations disturb delicate states. High-energy radiation can deposit unwanted energy inside a processor. Even tiny fluctuations in electrical or magnetic conditions can damage coherence. For this reason, one reliable logical quantum bit may require many physical quantum bits. The exact overhead depends heavily on the hardware, the quality of the physical operations, and the error-correcting code being used. For demanding fault-tolerant computation, the number can become very large. The difficulty is not merely building more quantum bits, they must also be good enough. If errors occur faster than the correction system can identify and manage them, increasing the size of the processor simply creates a larger noisy machine. This is why quantum computing is not expected to replace classical computing for every task. Quantum advantage is problem-dependent. Certain problems involving quantum simulation, factoring, search, optimization, chemistry, or mathematical structure may benefit from quantum methods under suitable conditions. Many ordinary tasks will not. Writing a document, displaying a web page, adding a column of numbers, storing photographs, or running most everyday software does not become automatically superior merely because a processor is quantum mechanical. Classical computers also remain essential even inside a quantum computer. They generate control signals. They compile quantum circuits into hardware instructions. They adjust laser and microwave pulses. They analyze calibration data. They decode error syndromes. And after the quantum processor is measured, classical computers process the resulting information. The two technologies are therefore more likely to work together than to exist as simple rivals. And throughout all of this engineering runs the same physical problem that appeared with Schrödinger's cat. Decoherence. A quantum computer works only while the relevant alternatives remain coherent enough to interfere in the intended way. If the environment obtains too much information about the state, that coherence is damaged. The processor begins to lose precisely the quantum behavior that gives it any advantage. There is something almost pleasingly circular about this. The environment explains why we do not see chairs, cats, and coffee cups wandering around in obvious quantum superpositions. Quantum engineers then spend enormous effort cooling, shielding, isolating, correcting, and controlling their machines so that carefully chosen superpositions do not suffer the same fate. A quantum computer is therefore not a magical machine examining countless universes and returning whichever answer we prefer. It is something more delicate. It is an engineered system in which probability amplitudes are prepared, entangled, rotated, phase-shifted, and recombined, so that interference changes the likelihood of what will eventually be measured. The process succeeds only when those fragile quantum relationships survive long enough to be useful. And that returns us to the strange state at the centre of all of this. Superposition feels almost impossible when judged by the world of ordinary experience. Yet in the laboratory it can be created. Its phase can be measured. Its interference can be controlled. Its destruction can be observed, and increasingly it can be engineered as a computational resource. The state that seems as though it should not exist is not merely tolerated by nature. At the quantum scale, it is something nature allows us to use. The world around us still looks wonderfully definite. A book rests on one part of the table. A lamp is either glowing or dark. A person walks through one doorway rather than several at once. The moon follows one visible path around Earth. And if a cat is asleep at the end of the bed, there is rarely much uncertainty about whether it is also simultaneously somewhere else. After everything quantum mechanics has shown us, that ordinary certainty can seem almost suspicious. But the classical appearance of everyday reality does not mean quantum superposition simply vanishes when objects become large. The deeper lesson is that large objects are extraordinarily difficult to isolate. They exist inside an environment that is constantly interacting with them. Air molecules collide with their surfaces. Photons scatter from them. Thermal radiation is emitted and absorbed. Internal vibrations, electrical activity, chemical reactions, and countless microscopic motions continually create new correlations. The quantum rules are still operating underneath. What disappears from view is the easily observable coherence between dramatically different alternatives. That distinction is essential. A coherent quantum superposition is not the same thing as ordinary uncertainty. If a playing card lies face down, we may not know what card it is, but the card itself has one definite face. Our ignorance does not create interference. Quantum superposition involves probability amplitudes associated with different alternatives. Those amplitudes possess relative phases, and because phase matters, the alternatives can interfere. They can reinforce one another. They can cancel one another. They can change the probability of an outcome in ways that cannot be reproduced by simply assigning ordinary classical probabilities to hidden possibilities. That difference is what makes superposition physically significant rather than merely mysterious language. The path toward this idea began long before physicists had a complete quantum theory. Thomas Young showed that light could produce interference. James Clerk Maxwell gave light a powerful classical wave description through electromagnetism. Then Max Planck and Albert Einstein helped expose the limits of that picture by showing that energy exchange could occur in discrete quantum units. Louis de Broglie suggested that matter itself should possess wave-like properties. Clinton Davison, Lester Germer, George Paget Thomson, and others helped confirm that electrons could diffract and interfere. Erwin Schrödinger developed wave mechanics. Max Born connected the wave function to measurement probabilities. Paul Dirac helped place quantum states into a more general mathematical framework. And gradually, the idea of superposition stopped looking like an optional interpretation of a few unusual experiments. It became part of the basic structure of quantum mechanics. The same principle appeared in different forms. A particle could have amplitudes associated with different paths through an interferometer. A spin state could be definite relative to one measurement direction and a superposition relative to another. Atoms could occupy coherent combinations of internal states. Photons could be prepared in different polarization superpositions. The details changed, but the underlying rule remained. Quantum alternatives can coexist within one coherent state and influence one another before a measurement produces a definite result. That last part created one of the deepest conceptual problems in modern physics. If the Schrödinger equation allows a superposition to evolve smoothly, why do measurements present us with one outcome? Erwin Schrödinger made the tension impossible to ignore with his famous cat. The cat was not meant as a cheerful proposal for experimental biology. It was a warning about what happens if quantum superposition is allowed to spread without a clearly defined boundary. A radioactive nucleus becomes correlated with a detector. The detector becomes correlated with a mechanism. The mechanism becomes correlated with a living or dead animal. Treat the entire arrangement quantum mechanically, and the state seems to contain distinct macroscopic alternatives. The point was not that ordinary cats wander around in obvious coherent combinations of life and death. The point was that quantum mechanics itself did not provide a simple, universally agreed location where the strange description must stop. Decoherence explains much of why those large-scale superpositions are invisible. When different components of a quantum state interact differently with the environment becomes entangled with them. Information about the alternatives spreads outward. The relative phase information becomes distributed through an immense web of correlations. For someone examining only the original system, interference rapidly becomes inaccessible. The system begins to behave almost like a classical statistical mixture. This is an enormous part of the reason everyday reality appears definite. A macroscopic object is being continually monitored by its surroundings. Its location is recorded redundantly in scattered photons, molecular collisions, thermal radiation, and countless other interactions. Widely separated alternatives therefore lose locally observable coherence extremely quickly. But decoherence does not quite settle everything. It explains why interference between macroscopic alternatives disappears from practical observation. It does not, by itself, explain why one unique outcome is experienced. If the complete system and environment continue evolving according to standard quantum mechanics, the global state can still contain correlated alternatives. This leaves room for different interpretations. Some descriptions introduce collapse as a real or effective part of measurement. Hugh Everett III proposed that universal quantum evolution continues without fundamental collapse. David Bohm introduced definite particle configurations guided by a wave function. Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber proposed spontaneous objective collapse. Roger Penrose has explored the possibility that gravity might somehow make sufficiently different mass distributions unstable in superposition. Other approaches reinterpret what the quantum state itself means. None has yet achieved decisive experimental victory over every major alternative that reproduces the same standard quantum predictions. The remarkable thing is that this interpretive uncertainty has not prevented increasingly ambitious experiments. Superposition has been demonstrated far beyond isolated electrons. Atoms can interfere. Neutrons can interfere. Large molecules containing many atoms can produce matter wave patterns. Trapped ions can be placed in engineered combinations of internal and motional states. Electromagnetic fields can be prepared in cat-like quantum states. Superconducting circuits can display coherent collective electrical behavior involving enormous numbers of participating electrons. Researchers continue trying to extend quantum control toward larger mechanical systems. There is still no experimentally confirmed mass, size, or complexity at which standard quantum mechanics simply announces that superposition is forbidden. What changes dramatically is the difficulty of keeping the environment from discovering the alternatives. That difficulty becomes especially clear in quantum computing. A quantum computer does not succeed because it somehow reads every possible answer from a superposition. Measurement will not provide such generosity. Instead, quantum algorithms exploit the structure of superposition before measurement. Amplitudes are prepared across different computational configurations. Quantum gates modify their magnitudes and phases. Entanglement creates correlations across many quantum bits. Interference then suppresses some outcomes while enhancing others. A carefully designed algorithm increases the probability that the eventual classical measurement reveals useful information. Peter Williston Shaw's factoring algorithm and Love Kumar Grover's search algorithm demonstrate different versions of this strategy. Neither works by simply asking every possibility for its answer and collecting them all afterwards. The useful resource is coherent control. And that creates a rather beautiful symmetry. In the ordinary world, the environment is constantly hiding quantum superposition from us. In a quantum laboratory, engineers spend enormous effort trying to prevent that from happening. They cool systems, they remove surrounding gas, they shield electromagnetic disturbances, they control lasers and microwave pulses, they correct errors, they reduce vibrations, they isolate quantum bits from the outside world while still finding ways to manipulate and measure them. The environment turns quantum possibilities into classical-looking behavior. Quantum technology attempts for a little while to hold that process back. This is why superposition is much more than a strange corner of physics reserved for philosophical discussions and unfortunate imaginary cats. It is built into the theory that explains atoms. It helps underlie chemical bonding. It shapes the behavior of light. It appears in matter waves. It allows interference. It is central to the manipulation of quantum information. And beneath the familiar solidity and definiteness of the world around us, the same quantum rules continue to operate. The classical world is not necessarily a separate world with different fundamental laws. It can emerge from quantum systems interacting so strongly with their surroundings that coherent alternatives become inaccessible. Superposition therefore occupies a peculiar place in our understanding of reality. Its behavior can be predicted with extraordinary accuracy. It can be created deliberately. It can be destroyed. It can be restored under suitable conditions. Its phases can be manipulated. Its interference can be measured. its fragility can be engineered into useful technology. And yet the deepest question remains surprisingly quiet. What exactly is the quantum state describing before a measurement gives us one definite result? A collection of real alternatives? A branching physical reality? A wave guiding definite particles? A mathematical expression of expectations? Something relational between systems? Or some deeper structure we have not yet understood? Quantum theory is remarkably successful at telling us what these impossible-seeming states will do. It is less unanimous about what they ultimately are. And perhaps that is what makes superposition so enduringly strange. The state that seems least compatible with ordinary reality may not exist somewhere outside the familiar world. It may be one of the fundamental reasons the familiar world exists in the form we see it all.